Okay, hello everyone. In the second talk of this new year, our speaker today is Artem Dudko from Invariant, surprisingly, and he will tell us something about invariant random subgroups and its connection to branch groups and characters and something very complicated.
Thank you very much for the introduction. So I'll talk about the relation between invariant random subgroups and characters, how to come from one to another, and specifically for branch and weakly branch groups acting on ordered trees. So I'll start with basic definitions of the objects which will be involved, and then I'll show some examples. I'll show the relation between objects, and I will formulate the results and, if time remains, sketch some proofs. So this is joint work with Rostislav Ilkorchuk. We just posted on Archive recently. So I will start with the definition of invariant random subgroup. So it means exactly what it means. For a countable group G, we consider the space of all subgroups of G, which can be viewed as a subset of all functions from 0, 1 to the group, which mark which elements are included in our subgroup. And so we can go with the product topology from 0, 1 power G. Then every element of the group acts on this space by conjugation. Group H is mapped to the conjugated group GH-G inverse, so we have naturally a dynamical system. And by definition, an invariant random subgroup, IRS for short, of group G is a G invariant Borel probability measure on the space sub of G. So it's a bit inconsistent notation. We will call measure invariant subject, but it's just notation which is traditionally used. Because measure defines a random subject with respect to this measure, random subgroup. Okay. The simplest example is given any normal subgroup H inside G, we can define just delta measure supported on this subgroup, a very simple measure. And this will be, by definition, an invariant random subgroup. Measure supported just in one subgroup. So invariant random subgroups, in this sense, are natural generalizations of normal subgroups. Another example, very important for this talk, given a measure preserving action of a group G on a Lebesgue probability space X mu, we consider pointwise stabilizers. Stabilizer of point X is just a set of element G acting trivially on this point. Then the push forward measure of the measure mu with respect to the stabilizer map is an example of invariant random subgroup of G. Just by definition, if you have a point X and it has stabilizer space X, the point G X will have stabilizer equal to the G of X G inverse, and that's why a measure preserving action of G on the space X mu will become, after push forward, an invariant measure on the space of subgroups. Okay? Yes?
Do people also study quasi-invariant random subgroups? or you only assume that you get equivalent measure?
I think so, but I haven't talked about results on this. But this is a natural question, I guess. So now the second object which we consider is characters and groups. Characters are functions satisfying a set of conditions. A function chi from group G to a complex number is called a character if first condition that chi of AG equal to chi of GH for any two elements. Or another word to say the same is that chi is constant on conjugacy classes of a group G. Second condition is positive definiteness. It means that for any finite number of elements, G1 and so on, Gn in group G, if we consider an n times n matrix with entries equal to chi of Gi, Gj inverse, it will be a positive definite matrix. And the last condition is just a normalization at the unit element, we assume that chi is equal to 1. And in the quantum notion, a character chi is called indecomposable if this condition satisfied, which basically means that chi is an extreme point in the convex set of characters. So please note that convex combination of characters is again a character, and extreme points in this set are indecomposable characters. Basic example, every group G admits two simple form characters, namely regular character, which is supported on the unit element of the group. So chi of E of the unit element is equal to 1 and 0 everywhere else. And the trivial character equal to 1 at each element of the group G. It's the fact to see that they are indeed characters. So characters arise from representations. If we have a unitary representation of a group G, that is, if we have a homomorphism from group to a group of unitary matrices, then we can just take a usual trace of a matrix, and this will give us a character. Now, in this talk, I will explain relation between some relation between the invariant random subgroups and characters. So these relations come from the following important example. Given any measure preserved action of a group G on a probability space X mu, we can define a function chi of G equal to the measure of fixed points with respect to the action of G. That is, we just take a set of point X such that Gx equal to X and calculate its measure. So one can show in various ways that this is indeed a character, it satisfies the above conditions. One of the ways is that one can associate to this action of G on the probability space X mu so-called groupoid representation, and trace of this representation will be exactly this function. But I will not focus on this in the talk. So what is the topic of the talk is the following maps from the set of invariant random subgroups to the set of characters. Given an invariant random subgroup, which is by definition a measure on the set of subgroups of G, we can associate to it the following two functions. The chi with index mu g is the measure of subgroups, set of subgroups, which are invariant with respect to conjugation by G. In fact, this is a function of the form given in the example 5. So we have group G acting on subgroups by conjugation, and this function is nothing else but the measure of fixed points under G in this case. And the second formula, the second function, psi mu of G, is the measure of the set of subgroups which contain G. So these two different formulas, they define characters. It's possible to show that they are characters in group G. Interesting, important objects in the space, in the spaces of various type are extreme points. In the space of invariant random subgroups, we denote by EIRS the set of ergodic invariant random subgroups. So this is a set of ergodic invariant measures. And in the set of characters, we consider the set of indecomposable characters, which we denote by I char of G. And so natural question, for instance, whether given ergodic invariant measure mu, the associated functions will be also extreme points, that is, they will be indecomposable characters. So we have two maps from ergodic invariant random subgroups to characters given by these formulas defined above. And natural questions are for a fixed group G whether these two maps coincide, whether they are injective. So I will refer to these questions later, so let me just quickly write them on the board somewhere. So it's the question, is it true that they will map ergodic invariant random subgroups into indecomposable characters? And is it true that actually they cover, the images cover I char of G? These questions were not studied yet in details, but the answers are known for several classes of groups. So examples, one of the most famous examples in the presentation series of infinite dimensional groups is the infinite symmetric group, which by definition is the group of finitary bijections of integer numbers. So we take positive integers numbers and consider all bijections which move only finitely many numbers. And decomposable characters and associated representations called factor representations. Were studied by many authors. So first they were described by Thomas in 1944 using some analytic tools. He studied so-called totally positive sequences or something like that. But then later, Vershek and Kerov given new proof of Thomas theory using the ergodic theory for the representation theory, and then Andrei Penkov gave another proof using representation theory and more algebraic approach. And relations were found with various other objects, for instance, random matrices. It's a really remarkable theory, representation theory of the infinite integral. Ergodic invariant random subgroups were described later by Vershek in 2012. And it is known that both indecomposable characters and ergodic invariant random subgroups of S-infinity are parameterized by two sequences of numbers, non-negative, such that sum is less or equal to 1 of these numbers. However, the maps chi and phi defined above do not completely respect this parameterization. So,
what do you mean by respect the parameterization?
We have naturally parameterized ergodic invariant random subgroups for each sequence alpha beta. We have new alpha beta corresponding measure on the space of groups. And also we have corresponding character chi alpha beta. And it turns out that the map capital chi defined before maps in ergodic invariant random subgroups, group of corresponding to alpha beta to a character chi which has parameters alpha union beta and 0. So not to the character chi alpha beta as expected.
Changes the parameterization.
Yes, it actually loses a lot. So we lose the second half of the parameters. And psi maps new alpha beta to this character, one half of two other characters, which is in general is not decomposable, for instance, because it's a combination of two characters. So the conclusion is that the map psi is injective on the space of ergodic invariant random subgroups. So the second question, a positive answer for psi. The map capital Chi sends ergodic invariant random subgroups inside the decomposable characters. So the question 3 has positive answer for capital Chi, but all other questions have negative answers. For instance, as you see, the maps are different. The map chi is non-injective because we have we're losing the second half of the parameters, etc.
Could you please, I have one question because I want to understand something.
Yep.
So, if we take only the set of where beta is equal actually to all zeros, it's 0, 0, 2, then it's injective, then it's equal, then everything goes perfect.
That's correct.
Okay.
That's correct. So the second half of parameters, they kind of screw things. Another example is full groups of Brattle diagrams. Previous talk, Olena Karpin was talking about generalized Brattle diagrams, but she also mentioned usual Brattle diagrams. And so there are groups actually naturally acting on them, called full groups, property diagrams. And they naturally act on the space of infinite paths, which Elena Karpel defined. In case when this action admits only finitely many invariant ergodic measures, you know them by mu1 and time k. Non-trivial characters as well non-trivial ergodic invariant random subgroups are parameterized by k tuples of non-negative integers. So this is our joint result with constant invariants. And the corresponding ergodic invariant random subgroups can be obtained using the stabilizer map taken push forward. Namely, we consider the tensor product of measures mu I power ni on the space x tensor power sum of n1 and 2 right, okay? And we take push forward, and this will be an ergodic invariant random subgroup. And using either map chi or psi, we can obtain a character. And all questions 1 to 4 have positive answers. So, in fact, even though the formulas are different, so just to recall, so chi, so we have character chi mu of G equal to measure of subgroups H subgroup G H G inverse equal to H. And this defines the map capital chi from invariant random subgroups to characters. And we have character psi mu of G equal to the measure of the subgroups containing a G. And it turns out, due to structure of these groups, one can show that this object will be actually coincident. They are injective and ergodic invariant random subgroups projected onto the set of indecomposable characters.
So this condition of having finitely many ergodic measures,
Mm-hmm.
so you can read it from the diagram, right? Or that's not.
Yes, for instance, if diagram have bounded, uniformly bounded number of edges, vertices, so if on each level we have at most d vertices, then there will be at most d ergodic invariant ergodic invariant measures on the boundary.
But in general, can you read it from the diagram, or because this is a sufficient condition, or?
Yeah, it's sufficient. In general, I don't think so. It's hard.
Yeah, I mean, there are some theorems. Sometimes we can say how many measures we have. If they come from subdiagrams, there are some criterions in terms of incidence matrices.
Thank you.
But in general, if you have a growing number of vertices, I guess there's no general condition which will tell you, right? Leva knows better about this.
Yeah. So if you want to, if you have finite rank, like you said, uniformly bounded number of vertices on each level, then we have not more the number of measures not more than rank. If you want infinitely many measures, then like in Pascal diagram, the number of vertices should, so there can be uncountably many measures. Yeah, and sometimes when we can see some subdiagrams which support measures, then we can say how many measures they are, looking at these subdiagrams. Like.
Okay. Thank you. Thank you very much. Another example, kind of extreme. There are groups which admit only two indecomposable characters. Shown in the beginning, the trivial character equal to 1 everywhere, and the regular character equal to 1 at the unit element of the group, and 0 everywhere else. Such groups also automatically admit only two ergodic invariant random subgroups supported at the trivial group, consisting just of one element, and the second is supported at the full group. So measure of the full group is equal to 1, and this such groups, example of such groups are the so-called Chevalier groups over infinite distant fields, showed by Ovchinnikov, commutators of Higman-Thompson groups. So for instance, this includes commutators of famous Thompson group, showed in joint work with Invariant. Another example is groups of rational points in certain algebraic groups over member field, result by Pekka and Francini. For them, properties 1 to 4 are trivially satisfied, well, because we have just two objects from each side, and it's very easy to check that we have these conditions. So the rest of the talk will be devoted to studying characters associated to invariant random subgroups on groups acting on regular rooted trees. Okay, so I'll try to explain what is the situation for this kind of groups. So regular rooted trees. By definition, a irregular rooted tree over some alphabet f of dilatance is a tree in which vertex set is divided into levels, the n greater than 0, and each level at the n is identified with f power n, that is with words of length n in this alphabet. And two vertices are connected if and only if one of them can be obtained from the other just by adding a letter at the end. So the picture is as follows. For instance, for d equal to 3, so the 0 level is just 1 point. Then we have first level. Say if our alphabet is equal to 0, 1, 2, then first level will be just one letter words. Second level will be 2 letter words, etc. And we consider groups of automorphisms of this tree. So the boundary of such a tree is a set of all infinite paths in D starting at the root 0. They are natural way identified with infinite ports over F. So this boundary is equipped with metric d of xy, standard metric d raised to power minus L of xy, where L of y is the maximal number of coinciding letters of x and y at the beginning. And so we obtain a counter set. The group of graph automorphisms of this tree, denoted by out of PD. And we notice that if we have a automorphism, it automatically preserves the root vertex, because it's the only vertex which has exactly the edges connected to it. All other vertices have d+1 edges connected to it. And this also implies that automorphisms preserve levels. They define some permutations of vertices on each level, and they define a continuous transformation of the boundary of the tree. It has a unique invariant Borel probability measure, just the Bernoulli measure equal to uniform measure on the alphabet f raised to infinity. Now we are interested in particular groups of automorphisms called branch and weakly branch groups. So let me explain what are these groups. Given a vertex V of our tree, we define by TV all infinite paths passing through V, or equivalently all words of the form VU. So here we have various infinite paths. And they form a subtree TV. Measure of the boundary is naturally d power minus n, where n is the level of the vertex. And for element G from the automorphism group, we denote by support G the set of vertices which are moved somewhere else by G. By definition, rigid stabilizer of vertex is the subgroup consisting of all elements of all automorphisms supported inside TV. So basically, list G of V is the set of automorphisms which act somehow inside the subtree, but act trivially everywhere else. And correspondingly, they act only inside the part of the boundary, the set of infinite paths passing through V. By definition, rigid stabilizer of level V is the product of all rigid stabilizers of each vertex of this level. So for each vertex we have its own rigid stabilizer, its own collection of elements, and we consider the product, which is a subgroup of G. Now definition. A subgroup G of automorphism group, which acts transitively on each level, meaning that for each vertex V and each other vertex W of level n, we can map by V to W by some element G. This group G is called branch if the rigid stabilizer of each level has finite index inside the subgroup G. So basically means that the rigid stabilizers are large inside our group G. And the group G is called weakly branch if rigid stabilizer of each vertex is non-trivial for every vertex V. So weakly branch just means that whatever high level M you take, whatever vertex you take, there will be some element of a group which will act only inside the subtree defined by this vertex and activity everywhere else. So this is kind of some richness condition of a group. Every branch group is weakly branched. It's not hard to see. For any weakly branch group G, the rigid stabilizers of two vertices V and W on the same level are conjugate. Due to this condition of transitive action and rigid stabilizer by definition of every vertex is non-trivial, and it's not hard to conclude from it that it will be infinite for all vertices V. So these are definitions of branch and weakly branch groups. Now, why are they interesting? So they play important role in group theory related areas. For instance, they contain examples and counterexamples to numerous conjectures. One of them is the so-called first Lippershire group G, which is the first example of finitely generated group of intermediate growths. It has many other interesting properties. So another example, there are actually continuum groups with pairwise non-equivalent growths, also constructed by Artem Dudko. Another example is the first example of amenable but not sub-exponentially amenable group, Basilica group G. It's weakly branch but not branch, and it's related to complex dynamics. It is the iterated monodromy group of the map z square minus 1. And one more example is the Lamplighter group can be also viewed as a group acting on rooted tree. And was recently showed that this is a counterexample of the strong clear conjecture. So maybe let me just draw one of these examples. Give a flavor. So the so-called Grigorchuk group G is generated by four transpositions, so four maps on the binary rooted tree, so d equals to 2. The element A just switches the first two branches of the tree and act tail preserving everywhere else, so just switches the first letter of infinite form. The element B acts as follows. It switches the branches of the second level, starting at the left vertex. Then here it acts trivially. So all the action goes along the rightmost path. What it does, along the right most path, it takes every third vertex and switches the two paths emerging from the left edge coming from this vertex. The element C is can be described as follows. It acts trivially on the left part. On the right part, we have a subtree, which is isomorphic to the initial tree, and there C acts as B. And similarly, we have element D, can be defined as follows. It acts trivially on the left hand side and acts as the element C on the right hand side. So this can be also written as using recursive relation, because from both vertices of the first level of the tree, we have subtrees isomorphic to the initial tree. So I think elements of this group are written as follows. So A acts as sigma transposition of the first level. B is acting as sigma D. C is acting as identity B, and D is equal to identity C. So what I've written here can be written using this recursive relation, referring to the sub-actions on the subtrees emerging from the first level, and they completely determine the action of this element of the whole tree. So this is just an example of how this group is described, how they are constructed. So, for instance, they are so-called self-similar groups because they have this kind of recursive relations. Okay, any questions? I hope I did not completely lost everyone yet, because this is a topic which is a bit far from the regular topics of the seminar. But nevertheless, so let me continue. For any integer n,
So this is related to a intermediate growth.
yes. So this is a group which has growth between the exponential and polynomial.
I remember you talking about partition of interval into pieces and special meetings.
Yeah. This is just another
This reflects.
another definition of this group. You can also describe the same by identifying the boundary of the tree modulo countable number of points with the segment 0, 1. Okay. So next, so for any vertex V, we can define by SV the symmetric group of all permutations of the set of vertices of the next level connected to V. Can we start this way? just if we have, so for instance, v equal to 3, we can take vertex v, and here we have a subtree, here we have 3 edges, and SV will be by definition just the group of permutations of these 3 vertices. And it naturally defines a subgroup of the automorphism. We just assume that we have an action which permutes edges, and details are remaining the same. And the group generated by all such symmetric groups SV is denoted by out fin of TD, group of all finitary automorphisms of TD. It is an example of branch group, which is hard to prove, being used as an exercise. So these are some examples, some motivation. Now we are interested in invariant random subgroups, branch groups, and weakly branch groups. They were started intensively by Ferenc Banks and Lars Lotos, who constructed a continuum of ergodic invariant random subgroup for any weakly branch group acting on a variable rooted tree. So their construction is the following. So we consider we have a group subgroup G of automorphisms. We can consider its closure in the group of all automorphisms and equip it with the Haar measure. This will be a compact group, so it will have Haar measure, for instance, left invariant. And given any closed but not open subset, which we denote by clone for short, we consider square brackets of C is the set of shifts of C by the action of group G bar. We equip it with the push forward measure, which we denote by lambda C. So having a measure on G bar, we obtain a measure on the collection of subsets of the boundaries of tree of this form. So for instance, if we say consider this vertex V on the second level of our tree and denote C as boundary of the corresponding subtree, so it's the set of all paths passing through V, or the set of all infinite boards starting at V, then because weakly branch groups by definition act transitively on each level, they will be able to move vertex V to any other vertex W. This is that level, and so in this case, this example, will be just the subsets of the following form. So if we have vertex V inside V2, this will be a set of all subsets of this form. So it will be a finite set. So this is an example. If instead, for instance, as a set C we take just one point, some point X, then what will we obtain is the set of all one-point subsets. So it will be naturally isomorphic to the boundary of the tree. So this is another simple example of this construction. But in general, we will obtain some continuum set with a measure in it and with a natural action of G. Then we can consider point-wise stabilizers of sets. So point-wise totalizer of a set A is just set of all elements G. Which are trivially on A. So Gx equal x for any x in A. And set stabilizer is just the set of all elements which possibly somehow act inside A, but GA as a set will be equal to 3. Okay, and so again we have some maps from sets to subgroups, and we can push forward the measure lambda c which we constructed using these maps to obtain invariant random subgroups, which we denote by mu c p and mu c correspondingly. So notice that here we write index as square brackets of C. That is the class of element C, the orbit of element of set C. Because for if you take different sets within the orbit, the result will be the same. So Banks and Toss proved that for any weakly branched group G and any clone open that is closed but not open subset C of the boundary of Dirac the tree, the invariant random subgroup using constructed using the point-wise stabilizer is ergodic and continuous. Moreover, given two clone open subsets from different classes, from different orbits, the corresponding invariant random subgroups are distinct. Thus, for any weakly branched group, we have a construction of continuum many ergodic invariant random subgroups using this construction. Now recall that for any ergodic invariant random subgroup, we have two characters associated with these formulas, also written here on the board. Then the question is, we take a set C, we use this construction to construct ergodic invariant random subgroups in two ways. Then we have these two ways for each IRS to construct a character. So what will we obtain as a result? So given a group G and a closed subset, we consider the four characters which we obtain using this 2 by 2 different ways. So to each subset we associate four characters. For simplicity we denote it by chi c character associated to mu c with map chi, k cp, etc. So here's an example of what happens with these characters. So consider a binary rooted tree, E2. Let V1, V2 be the vertices of the first level. As level capital V1. Let C be just the boundary of sub-tree emerging from V1. So this is our C. If you have a weakly branch group, acting on this regular rooted tree, so there exists an element A which moves V1 to V2. This is because by definition weakly branch groups are transitive on levels. And one can show that invariant random subgroup mu C, which is constructed using the stabilizer map, is concentrated at just one point, which is a subgroup consisting of all elements acting trivially on V1. That's because in this case, our space consists just of two sets. And this is exactly the stabilizer of either of them. So using stabilizer map from these 2 points, they go to one subgroup. So you can see that chi C of A equal to chi mu of A equal to 1. Because A as a trivial reason acts trivially in the subgroup. But if you consider the character psi C, so by definition, so we need to take measure of subgroups containing our element, in this case A. Since A does not belong to the stabilizer of the first level, we obtain that psi C of A equal to 0. This is just an example showing that psi C can be distinct from psi C. Another example, consider element B, so it should be rigid stabilizer of G, if we group G here, of vertex V1, not equal to identity. So we just take any element B which somehow acts inside this subtree and acts trivially outside. Notice that if we take point Y stabilizer, then we obtain from these two sets two different subgroups. By definition, we obtain the subgroup rist G of V1 and subgroup rist G of V2 correspondingly. In this case, psi C with index P of B. So obtained using this formula, but now using mu from the point-wise stabilizer map. It is equal to 1 because B acts trivially on both of these stabilizers. For the first vertex V1, B belongs to this rigid stabilizer, so this was the group. For the second vertex V2, so rigid stabilizer of the second vertex acts inside here, so it commutes with B, and again we obtain its identity, so B preserves them. And so using this first formula, we obtain full measure on these 2 points. So we obtain 1 as value of character on B. But if you take psi, because element B belongs to first rigid stabilizer, acting here, but does not belong to the second, we have here measure 1/2. So we have measure on 2 points, measure of 1 point and 1/2. So this is just some basic examples to illustrate these different formulas and the notion of weakly branch group. Any questions?
So maybe one question, because like in these examples, and I know that C is very simple, but
Yeah.
in the end, it seems that the structure of gamma, or sorry, of G,
Right.
does not play any role.
In this case, yes, because of simplicity.
Okay, you have these exist, but okay, in general, this will happen that somehow the concrete choice of gamma will give you different behavior.
For some specific example, it might, but in general, in the proofs of our results, we use just properties of weakly branch, properties branch, so we proved some statement for the whole class. But specifics might depend on particular choice of group. Okay. So we showed, it's not hard to show, formulas for these characters which we denoted. So C of G, which will be just the measure of subsets inside the orbit of C. So P such a stabilizer of B coincides with the stabilizer of GB. It turns out that for weakly branch, the characters phi C and psi CP will coincide. And it will be just equal to the measure of sets B, which are setwise fixed on G. And finally, the characters psi CP of G equal to the measure lambda C of sets B, on which G acts trivially. That's identity. So we wrote each of the characters inside convenient inside as the same measure lambda C of certain collection of subsets. So another example illustrating these characters. Showing their properties. So with more complicated example, consider t equal to 3. So we have 3 vertices on each level. Denote alphabet by 3 letters A, B, C. And let C be the union of all subtrees of emerging from vertices of the form C power n A. N greater or equal to 0. So C will contain this subtree. It will also contain this subtree. And this one subtree, and so on. This all is inside C. Consider element G, which is just transposition of P A and P B. So G will just switch in this two. Letters at the beginning of word. And also for each letter from the set ABC, from each letter X, we denote by HX cyclic permutation of the subtrees emerging from this letter. And assume that our Yuki branch group contains all these elements G, HA, HB, and HC. So for instance, the group of all finitary automorphisms is of this form. Then we can show that chi C of G is equal to 1/3. So let's see why this is. So we can permute our set C in various ways. So the question under which kind of permutations, under which kind of actions we will have a set P for which we have stabilizer of B equal to stabilizer of G B. So if we have this kind of set, and here we are allowed to make some mess, we assume that this part are shifted some way, then this is true. Stabilizer of B will be coinciding with stabilizer of GB. Because what does it mean that we have that our map is stabilizer B? It means that it does not move these two vertices. And here also there are some conditions about which we don't here. Now this means if we have another set which has this form, something with this form, then we'll have the same stabilizer. However, if this vertex is moved by an element inside A to A and B, then it's not hard to see that the stabilizers of B and GB will be different. It does matter where we have our messy kind of part. And where we have, so if we have here moved this left part, we have a complicated structure. And here we don't have anything. Then of course stabilizer of this set will be different from stabilizer of GB, because stabilizer of this set can have anything acting here. and vice versa. So I hope it gives an idea why we have this formula. So we have probability 1/3 that our set will be fixed by element G.
May I ask a question? Because one thing which is not clear to me. So you have a full understanding of C. That's fine.
Yeah, it's
But,
something.
but now in this example, let's just think about this example.
Yeah.
But now you want to ask about something which happens in this closure.
Yeah.
Which depends on the choice of G.
Yep.
So why does this argument work? Because you
Uh-huh.
just tried to kind of convince us that we can just look at what it does to elements of C.
Yeah. So here basically we just subdivide our set by square bracket C into collection of subsets of the same measure, depending on where we have this part where we have the whole subtree contained in it, and where we have nothing. So we have six different situations. And using that our measure on the closure of the group G is invariant, it's shift invariant, and the fact that our group acts transitively on levels. So we can show that these parts, they have the same measure. So here we don't know what exactly happens, but in total the collection of all subsets inside square bracket C, which has this form. Here we have anything obtained by shifts. In total, it will have measure 1/6. It's one control just because of invariance of the power measure. Okay, so I was pretty slow. I guess I didn't come to the results. Okay, so this example just shows that the characters described here can be pairwise distinct. Finally, I can formulate some results. So assume we have a weakly branch group acting on a deregularity tree. Then there exists a continuum set of different classes of this form, for which the corresponding measures mu C will coincide. So these are measures obtained using the set-wise stabilizer. And the characters chi CP and psi CP also will coincide. But the measures mu CP, so it's not written, measures mu CP will be pairwise distinct. So we have a continuum distinct invariant random, ergodic invariant random subgroups mu CP, for which the corresponding character will be the same. So basically here we show that chi is highly non-injective. There is a continuum ergodic invariant random subgroups which are mapped by chi to the same character. On the other hand, there's also continuum of classes for which the corresponding characters are distinct and indecomposable in case G is branch. In particular, we obtain for every branch group a continuum of distinct indecomposable characters. So this is different, for instance, from the situation of full groups of quartic diagrams mentioned before, for which we have countably many characters in case we have finitely many invariant measures. So here we obtain continuum. Okay, this is one result. Another result, we show that for any weakly branched group acting on a diagonal tree, when any two distinct classes, the characters psi, c, p are distinct. So these are characters which are obtained using pointwise stabilizer of random set, and then applying to it this map. So this gives partial answer, positive answer to this second question about psi. So psi is injective at least on the collection of the invariant ergodic random subgroups of this form. So we see that psi and psi are different and very different in this sense. Chi is highly non-injective, but psi is injective at least in this set. And actually, I do not know examples for which for any groups for any kind of ergodic invariant random subgroups. I don't know examples in which psi will be not injective. So I don't know two different ergodic invariant random subgroups which are mapped to the same character via this formula. Okay, another example, an application is related to hyperfinite factors. So I don't have too much time to talk about this, but for those who know about this object-operator algebras, so we have a unique hyperfinite to one factor of Neumann. If so, we denote by U of R its unitary group, and by out of R its group of automorphisms. So for each countable minimal branch group G, as a consequence of previous examples, we obtain a family of embeddings of this group into U of R, which belongs to pairwise distinct orbits under the action of out of R. So just some application to embeddings into hyperfinite factors. So another topic important for the question of this maps from invariant random subgroups to characters is the topic of non-free actions. Given a countable group acting by measure preserving transformation on a vector probability space X sigma mu, Anatoly Beshik introduced so-called total non-free action, which just means that the sets of the form fix of G, sets of fixed points with different elements, generate modular zero back measure the whole sigma algebra of this space. And the second notion is extremely non-free action, meaning that the stabilizers of points are almost surely pairwise distinct. He showed that for countable groups, these notions are actually equivalent, and so there was interesting story for us. So Anatoly Beshik conjectured that the character chi of G is equal to measure of fixed point is indecomposable if and only if the action of the group is totally non-free or equivalently extremely non-free. And he wrote a statement in his paper and gave a sketch of proof. When we were working with Ostap Grigorchuk on characters of branches between branch groups, we read his paper, we wrote a paper and wrote in particular proof of these Vershik statements, our proof. But then later, when the paper was already in process of reviewing, someone, I think Becker, pointed out to some inconsistency in our proof. We read it more carefully, thought about it, and then we showed that actually it's false. We showed that the statement is false in both directions. We found a mistake on our proof. So there exist totally non-free actions for which the character is not intercomposable, but also there exist characters of this form for intercomposable characters of this form for which the action is not totally free. So when we studied intercomposability, we had to come up with new notions. And we came up with two new notions of non-free actions. So one of them is as follows. So for any measurable set A, we consider the subgroup GA of elements which are supported, modulo zero measure, on the subset A. And we say that the action of G on the space X sigma U is perfectly non-free if there exists some countable collection of measurable subsets for any A from this collection, and for mu almost every point X inside A, the orbit GAX is infinite. So we consider, say we have a space, a segment, for simplicity, say this is our A. So we consider all elements acting inside A, acting to the outside. And the condition is that for any point X, for almost any point X inside A, the orbit of this point under group of the elements will be infinite. So we want a countable collection of this kind of sets generated sigma. This is our notion of perfect non-freeness. It's stronger than Vershik's notions. And we show that, in fact, this new notion is sufficient for character to be indecomposable. Namely, for any ergodic, measure-preserving, totally perfectly non-free action of a group G, the associated character will be indecomposable. So total non-freeness and extreme non-freeness turned out to be not sufficient. We needed to come up with something stronger. And
Wait. What about the other direction?
The other direction is more complicated, so we don't know what kind of property indecomposability of this character implies.
But do you know that this doesn't? So you have a counterexample in the other direction here?
I think so. I think that if you take a free, extremely, essentially free action, if you take essentially free action, so each element moves almost all points, and so there will be no non-trivial sets of this form. If we take set A, which has measure less than 1, then the subgroup GA will be trivial, and so this will be just 1 point. So We will not be able to construct even not one non-trivial set of this form. I'm not saying about collection, countable collection. But the character, the associated character for essentially every action will be equal to the regular character. It will be equal to 1 at the unit element, but 0 everywhere else. And it is indecomposable if and only if the group is what is called infinite conjugacy classes group. So there are examples, right? There are counterexamples. Okay. So let me. So don't have time for this details. So we can give some conditions, sufficient conditions of indecomposability of character size C using total non-freeness and so show that these conditions are sufficient for the indecomposability. And let me skip the details because I don't have time. So most importantly, we showed that for any branch group G acting on the regularity tree TD and any closed set with empty interior, the action of G on the class C by translations is perfectly non-free, and the consequence we obtained that the character is indecomposable. So this gives us partial answer to question 3 here for the group for the map side, at least on the periodic invariant random subgroups of this form. We obtain indecomposable characters, so at least partially inside I chart of G. So we showed that condition of empty interior cannot be dropped. So let me just quickly draw the picture of this example. So we consider the ternary rooted tree, and we consider vertex V on the first level and point X from the complement. So somewhere X here we have point X, and we denote by C the union of this part here and the point X. This will be our set C. And one can write formulas for the character size C in this case, and using just character theory for infinite for finite symmetric group on 3 elements, we can obtain that this character will be decomposable, will not be decomposable. So here the set C has non-empty interior, and this shows that condition of empty interior in general cannot be dropped if you don't impose additional conditions. And finally, we also construct an example of subset C and weakly branch group for which associated character C, size C equal to size CP decomposes into an integral of continuum many indecomposable characters. So this shows that for a weakly branch group, it is possible that here in the image actually we will have character which is integral of continuum many other characters, so it will be very strongly not indecomposable. So in general, this shows that we have very rich picture here for the invariant subgroups and characters, and the answers to the question are complicated and needs to be started more. Okay, that's all I wanted to say. Thank you.
Any questions, additional questions, comments, perhaps from the online participants? Yeah, Elena, thanks for the talk. If not, let's thank Artem again. I have no idea.
How do you see the embeddings into the unitary group of R? How do you see these embeddings in the unitary group of R?
Just because we have a unitary representation.
No, sure, no, that part I understand, but how do you